So 6.4, the fundamental theorem of calculus. There's a part 1 and a part 2 to this theorem. The first part. If f is a continuous function on a given interval, a to b, then the function, capital F if you'll note, is equal to, now this is from a number like -1 to the variable x, right? So we don't really know what that ending point is. It's a variable. So for the small function. Now what the heck does that mean? We'll find this out in a minute. Then this function, capital F of x, which is the integral from a to x for the small f function, for the original function, and it has a derivative at every point in between a and b. And the derivative of this capital F is going to be equal to the derivative of that integral expression. Well, what does it give you? Well, the derivative of an integral, it's like doing opposites, like multiplication and division, will just give you the integral inside. Now, something you might want to add. Basically, what this is telling you, and I've mentioned this before, is the derivative of an integral, you're doing inverse operations in a sense. It just gives you whatever you had inside. Now, you'll notice that the way this was written, it has a t in here. F of t dt. We just tend to do that, but we're putting the variable x into it. So we end up with f of x. Now that's not too, just changing variables. That's not too bad. Now what does this capital F refer to? We've talked about it, and it's the idea of an antiderivative. Now just jot this down first, if you want here. This capital F is an antiderivative. I'm running out of space there. Antiderivative derivative of small f of x. That's what I'm talking about here. Okay? Now, because we said we know a thing or two about antiderivatives, it's thinking of the derivative backwards. Now, an antiderivative could mean all kinds of things, and we talked about antiderivatives, for example. Now, I'm going to erase this, but just to, so don't jot this down. If I tell you the expression 2x is your answer to a derivative, like to a derivative question, what was that from? X squared. Okay. X squared is an antiderivative. However, what if you did the derivative of x squared plus 3? What's the answer? It's also 2x. X squared minus 8. These are all antiderivatives of 2x, the simplest antiderivative. So if you're asked for just an antiderivative, just say 2 or x squared for this expression. Now, of course, we're going to see it later on with the integral and so on. But we will assume if you're asked for an antiderivative, come up with the simplest one, which would be x squared plus 0 in this case, right? Now, so basically what we're saying is if you're doing the derivative of the antiderivative, you're just getting the original function back. That sounds almost silly. Now, if this is the what we had here, the antiderivative, right, x squared, what's the derivative of that with respect to x? 2x. So you see what I started with was 2x. What's its antiderivative? X squared. What's the derivative of that? It's 2x. It's a circle argument, right? That's what we're saying in a sense there. However, we've got to keep this in mind with the integration here. Now this is important because, let's try an example. We're going to get a shortcut. The function needs to be continuous, otherwise this theorem doesn't apply. And we'll use the fundamental theorem, part 1, to find derivatives and our knowledge of antiderivatives to show why it works. Now, I'm going to show you the long way first. Just like, you know how when you guys are completing the square, then they say, hey, there's a quadratic equation to do this, right? And it's a general form. Well, this is the sort of thing, completing the square is actually, you know, it's not that long, but if you can jump right to the formula, it's a little quicker. Same with this. So first, though, we're going to use the long way, and I'll label it as the long way. We'll look for the shortcut after. So this example here kind of looks like this, doesn't it? Okay. Now the idea of this here, and if I'm just looking at this without knowing too much about this, if I say d by dx, I'm going to show you a new thing with notation here. Or, no, I won't. I won't do it right yet. Let's see here. What? Yeah, I will do this notation thing here. What is the easiest antiderivative that gives you cosine? Sine of t in this case. The sine function at t. Now, this is the antiderivative inside the box, and I'm still going to then apply this. Now, I want you to get used to seeing it like this, because when we get more complicated things, this applies here. So all this means is, remember how we then took the antiderivative with x plugged into it minus the antiderivative with pi halves plugged into it. We were doing that on Thursday, Friday. You guys weren't. Now, do you get this idea, though, of an antiderivative? What you would have, if you did the derivative of sine of t, you would get an answer of cos of t. Okay. I'm looking at you guys because you guys missed out a bit. So, all I have to do now is, in the brackets, I'll keep the derivative operator outside, is say that this is the sine of x subtracting the sine of pi halves. Okay? So that's line's equal to the next line. So you can use equal signs. That's equal to the original expression. Now, we've got to pull that operator through this. What's the derivative with respect to x of sine of x? Cosine of x, right? Hey, didn't we say that when we figured this out? Okay, so this is the cosine of x. Now, sine of pi halves. Now, I hope you can do that. Sine of pi halves is 1, right? But let's say it was the sine of pi over 18. All I know, I don't know what that is, but I know it's a number, right? What do we call a number? A constant, right? What's the derivative of a number? 0. So this is the cos of x minus 0. It's just the cos of x. Okay, as long as the x is at the top here, this will be the answer here. What could be a shortcut then? If you know it's from a particular number unto a variable like x.
Taking the function.
Just take the function out, because you're saying, yeah, the derivative of the integral of this expression, it's just the cosine, but you put in your x instead of t. Because x was the variable you're now operating. Does that make some sense?
In the 6.3, derivatives and integrals are opposite functions.
And we said that, but we haven't formally, yes. And this is building on to that in a more formal way. So yes. So we could just skip the middle and just jump to this. Only if it's number 2x. Now let's just see if this works here. And we'll do this one the long way as well, and see if our hypothesis works, if we could just skip. So according to this, our shortcut should give us x squared, right? Now how does this work? Let's get some practice though, the long way. T squared, the antiderivative, we would have had, it would have been t cubed, but then you'd need a 1/3 in front of it, because when you do the derivative of t cubed, 3 over 3 t squared, okay. And I'm going from 5 to x. I'm just practicing where you place in an antiderivative into the bracket. Then I actually do the subtraction. Or set it up, I don't actually do it. 1/3 x cubed. I plug in the x, subtract 1/3 times 5 cubed. When I do the derivative of this expression, the derivative of 1/3 x cubed is x squared as we hypothesized. Then the derivative of the 1/3, 5 to the power of 3, it's 125 over 3, but you don't need to know that. You just say, hey, that's a number, 0. Do we now see how to go directly to that answer? That's what I want you to see, okay? This only works, as mentioned before, if it's from a number to the variable x. Okay? If it's the other way around, x to the x on the bottom 5, you'd have to switch things around. So if this was this way, that's not exactly the same. So if I flip-flop and I have, t squared dt and whatever. If I want to flip-flop that, what happens? What's our rule if I want to put the x on the top and the 5 on the bottom? Negative expression. And that's one of the rules from point 3. Now, so you can get around that if that happens. What about if we have, well, x squared or 3x or something like that at the top? 0 to x squared. We need to use the chain rule since the upper limit doesn't match. We're going like d by dx, not d by dx with a square root, right? This is a single x, this is an x squared, so that makes a difference. Now we're going to use the shortcut here, the shorter cut, meaning I'm not going to actually plug in sine of x squared, or the antiderivative and so on, and then the minus cosine, negative cosine, I guess, of 0. We're going to skip to it. If this was x squared, or I mean if this was just plain old x, let's just think. What would this be if this was plain old x? This would evaluate to be sine of x. But it isn't. So we know sine of x squared. Okay, we know this. Now think of it this way. We've done the derivative of the outside of the function. Chain rule says then you got to move to the inside of the function, right? Which means, no, what's the inside of the function? Just the x squared, which is derivative, 2x. I wonder if I'm on disappearing. Oh, I was going to put d by dx at x squared, but 2x. I'm doing this in the order that you'd be thinking. You'd probably be most likely to see an answer like this, 2x sine of x squared. Now that x squared, let's get this clear too, if you ever had to plug something in. When you see this, just notation-wise, I want us to all be certain. This is really 2x sine of, if you were to use brackets, x squared on the inside of the sine function, right? This is not 2x sine of x squared, which would imply then you'd put sine squared x. That's equal to 2x sine squared x. Notation. Now, that's just a warning there. If you're clear on that, don't jot that down. But You guys see the difference? There's no brackets given. Assume this is only operating on the x squared. Okay. That's if you have to evaluate. Now, you'll get some practice with those kind of things. I'll give you a little more practice. I've already mentioned something like this. You need to change the sign of the derivative and reverse the limits if the upper limit is a constant, but the lower limit is not. So the old flip-floppy, right? As I mentioned, if I want to put the x on the top, I got to use a negative sign in here. So I'll move the negative sign right to the front. Now, boy, am I glad that we don't have to find the antiderivative of that expression, because I don't think you guys know what it is. I don't off the top of my head. We don't have something that 4t times cosecant of t, right? Hey, Ms. Clark.
Hi, will you send me a debt?
We just fill her in. Negative sign is built into the front. 4x cosecant x. Okay? We didn't have to know the antiderivative. One. You'll notice this expression, I have 4x and I have x cubed. This is garbage, I think, because there's no number. So we need to split the integral into two parts, because neither limit of integration is a constant, like 2 or something. So we can just call it a number, a, any old number. I don't know which one is in between 4x and x cubed for this given function. So we're just going to use a. We're not going to actually use a number, but you can pretend it's 2 or 0 or 1 in your head if you wish, or any number of your choosing. Doesn't have to be an integer. So we're going to use the rules that we figured out in point 3 or played around with the other day. We're going to say this is equal to this expression, d by dx, I'm going to just put this outside, of, now, I'm going to do this in 2 steps here. If you get nifty with this, you can I don't know the antiderivative of this one, by the way. But here's what I'm doing, and then I'm saying plus the derivative from a to x cubed. Now, do you see what we have there? As long as these two things match each other, we're good. By the way, the d by dx in front, it doesn't really matter because I could have factored that operator out and just put a big bracket here if I didn't have this one here. Same thing, right? That's how we saw the rule before. But, okay, as long as I understand that, and then I understand I need the a on the bottom, the 4x, to switch spots. So I'm going to just put a negative sign in front of that. And if you get good with this stuff, you can just do that in one step. I'm fine with that. So negative d by dx. So this is the exact same expression. Good gravy. Okay, once I have that, I'm cooking with gas because I can do this. We come up with the new expression, and we're going to remember we have to use the chain rule, the derivative of the inside with this. This 4x is going on the inside, x cubed is going on the inside. So the first thing is negative, because of the negative sign in front of the derivative operator. 1 over, if you want to put just negative 1 on the numerator, 3 plus, oh, it's going to blow. You okay, Ming? You feel safe? 4x, then I do the derivative of the inside. I'll show it as a separate chunk. The derivative of 4x times 4. I put that in brackets, don't just list the number 4 floating in space. Plus 1 over 3 plus 5, plug in the x cubed. Make sure it looks like it's an exponent inside an exponent there. Then the derivative, 3x squared, the derivative of the inside. You can leave this. I wouldn't expect you to simplify that. The idea is the question. Here, for example 5, this trick here. Constructing a function with a given derivative and value. Find a function, y, that's some function of x. It's got x. With this derivative. Okay, so we know what the derivative is going to equal, tan of x. That's the answer. And it satisfies this condition. When I plug 3 in, it's going to give me 5. And I was like, what? Let's see this, though. Look at this. And we'll see why it works. F of x, here's a function from 3 to x. Make it as simple as possible. Tan of t dt. After that, plus 5. Now, oh, you know what I forgot? No, I didn't. No, it's good. It's all good. This is the answer to the question. Why? Let's see if this works. What's the derivative? Is it going to give me tan of x? Well, if I do the derivative, so d by dx of this expression, you know, f prime, what's going to happen? The 3 part will disappear and I just get tan of x, right? And the derivative of 5 is 0. Now, do you guys see that condition's met? So if I needed to take the derivative of this expression, I guess that'd be for the whole thing here. I will get tan of x, agreed? Because it's just the same thing. What about the condition f of 3 equals 5? If I tried this, nothing to do with derivatives, f of 3, what would you replace the letter x with? 3. What is the area between x equals 3 and x equals 3?
0.
0 plus 5. That works, doesn't it? You see what I mean by a dumb trick? 0 plus 5. It works. This condition works too. Now, it's not a common problem that you're going to come up with, but with what you guys have here, you can do this first portion of the assignment. Well, that's odds too, okay? So only do 5 through 11 odds, 17 through 23 odds, and actually it's a fairly short thing because a lot of them you just look at and say it's the same function, put in the x. Okay? I will stop this.